In ancient Greece, mathematicians built their world on a single, absolute rule that everything in the universe could be measured and expressed as a ratio of whole numbers. They called these rational numbers. To them, any quantity, no matter how small, could be broken down into a clean fraction, like 3/2 or 7/5. To see how this system was supposed to work, we can look at a square with a side length of exactly 1 unit. It is the most basic, predictable shape in geometry. But when you draw a line from corner to corner, the Pythagorean theorem forces a specific result. 1 squared plus 1 squared equals the square of the diagonal. This means the length of that line must be the square root of 2. For the Greeks, the challenge was simple: find the exact fraction that equaled this root. If they couldn't, it meant their most basic geometric shape contained a number that their mathematical system couldn't describe. We can simulate their attempt to pin this number down by testing modern decimal approximations. On this number line, we start at 1.4. It's close, but it leaves an error of about 0.014. We can increase the precision to 1.41, and then to 1.414. The error gap shrinks rapidly, getting closer and closer to the target, but it never actually touches 0. When we look at the full expansion, 1.414, 213, 5623, and so on, the numbers never stop. Unlike a fraction, which eventually ends or falls into a repeating pattern, this sequence is chaotic and infinite. This non-repeating string of digits was the first evidence that the square root of 2 didn't fit the definition of a fraction. To see why this is a logical certainty, we can use a proof by contradiction. We start by assuming the square root of 2 is a fraction, p over q, and that this fraction is already simplified to its lowest terms. If we square both sides to get rid of the root, the equation becomes 2 equals p squared divided by q squared. Rearranging that gives us p squared equals 2 times q squared. Because p squared is exactly 2 times another whole number, p squared must be an even number. Mathematically, this means p itself must also be even. If p is even, we can replace it with 2 times k. Plugging that back in and simplifying the math shows that q squared also equals 2 times a whole number. Now q must be even as well. This creates a logical dead end. If both p and q are even, they both share a factor of 2. But we started by saying this fraction was already simplified and had no common factors. The original assumption that this number is a fraction is impossible. Even without a clean fraction, you can still try to find integer pairs that satisfy the equation through trial and error. Take the pairs 7 and 5, or 17 and 12. When we plug them into the formula p squared minus 2q squared, we get results of -1 and +1. As we test larger pairs, the results continue to oscillate. They jump back and forth between positive and -1, perpetually skipping over the 0 we need for a perfect solution. We can get infinitely closer to the square root of 2 than any physical measurement would ever require, but in our system of whole numbers, the exact value remains unreachable. This discovery revealed a massive gap in early mathematics. It proved that geometry could create lengths that simple arithmetic couldn't name. To solve this, mathematicians had to accept a new category: irrational numbers. These aren't just missing fractions, they are a different class of quantity entirely. This forced us to view the number line not as a series of isolated points or fractions, but as a solid, continuous medium, where every point, even the ones we can't write as ratios, is a valid number. Transitioning to this continuous number system allowed mathematicians to eventually model smooth change and motion. This shift in how we define real numbers provided the basis for calculus. Today, this value is a tool for describing physical space. In physics, when two equal forces act at a right angle, the resulting diagonal force is exactly the square root of 2 times the original magnitude. It is also used to stabilize data in machine learning. When initializing the weights of a neural network, We use the square root of 2 as a scaling factor to ensure that the signals passing through thousands of layers don't grow too large or vanish entirely during calculation. When we zoom out from a single 1 by 1 square, we see this number integrated into the digital and physical systems that surround us. The diagonal of the simplest shape in geometry contains a value we can never fully capture with fractions. It shows that even basic structures possess a level of complexity that forced us to expand our understanding of what a number can be.